for sure. So in group 13, we have boron. And I mentioned before that boron can become an ion or it could act and share electrons as a nonmetal. And that's because it's a metalloid. So it can act as either a metal or a nonmetal. It has some properties of both nonmetals and metals. The rest of the elements in group 13 are considered metals. And these metals aren't as good or aren't as reactive as group 1 and 2, but they're still good conductors of heat and electricity. They're not as reactive because they have to give up 3 electrons instead of fewer electrons. Group 13 metals tend to share electrons instead of forming ionic compounds, but they're not sharing electrons as in covalent bonds. They're sharing them in a metallic bond. So that we're going to talk about a third type of bond here in a bit. Now, aluminum is the most abundant metal in Earth's crust, and boron can actually be used as a cleanser. If you've ever heard of borax, that's a type of cleanser that has boron in it. Group 14, we have carbon as a nonmetal, and then you have silicon and germanium, which are metalloids. Tin and lead, of course, are metals. These metals will either gain or lose 4 electrons, or in the case of carbon, and sometimes silicon and germanium, depending on their bond type, will share electrons. In group 15, we have 5 valence electrons. Nitrogen, phosphorus, and arsenic can have oxidation numbers of plus or minus 3 and plus 5. It depends on whether or not what they're bonding with and how they're bound and how those electrons are shared. Now, nitrogen is a component of proteins, DNA, and RNA. It's integral as part of our biology. And phosphorus is part of the phosphate ion, which is a repeating link in DNA chain. And it's also part of ATP, which is where we get our energy in biological systems. Nitrogen is also 78% of the atmosphere. Now in group 16, you have all nonmetals with the exception of polonium, which is a metalloid. And with rare exception, oxygen gains 2 electrons to form a negative ion. Oxygen is the most abundant element on Earth and makes up 21% of the atmosphere and 50% of Earth's crust. And there are 2 allotropes of oxygen. We have O2 and O3. O2 is the elemental oxygen that we need to breathe, and I've mentioned before that O3 is the ozone that protects us in the stratosphere from the harmful rays of the sun. Now, ozone is highly unstable and it's reactive. So if it's closer to the surface of Earth, it's very, very toxic because of its instability and reactiveness. But we still have a purpose for it. We can use it to deodorize and sanitize. Now, metals and nonmetals react with oxygen to form oxides. We have sodium plus oxygen, and that produces sodium oxide. Whenever you see rust, that's the iron reacting with the oxygen. Carbon plus oxygen, that's carbon dioxide. Sulfur also gains 2 electrons when it reacts with metals or hydrogen. But when it's reacting with nonmetals, it can have other oxidation numbers. Halogens are active nonmetals. They don't exist as free elements in nature because they're also very reactive. They only need to gain 1 electron to form that negative ion. And the most reactive halogen is one with the strongest attraction for an electron. That would be fluorine because it's the smallest, so it has the greatest ability to attract and hold that electron. Now, the reactivity of the halogens decreases as you go down the group. The halogen reactivity is opposite of the alkaline and alkaline earth metal reactivity. Group 18, we have our noble gases. They have their complete octet, so they don't react easily. That's why they're called noble gases. The nobles did not associate with the commoners back in the day, so they kept to themselves. So noble gases were named because of how the nobility acted. Now, with the exception of group 12 elements in the transition elements, the transition metals have higher melting and boiling points than most of the main group elements. Melting points increase from rows 3 through 6, but they actually decrease from rows 6 through 12. It's a little different. Tungsten is the highest melting point at 3,410 degrees Celsius, and that's one of the reasons why it was used in our traditional light bulbs, because it had such a high melting point and could withstand the heat from the electricity going through. And mercury has the lowest at negative 38 degrees Celsius, which is why mercury is a liquid at room temperature. Transition elements, as we know, can have multiple oxidation states. We learned that with our stock system nomenclature. Iron, for example, has two different forms, 2 plus and 3 plus. Many transition metals have oxidation numbers ranging from 2 plus to 7 plus. Manganese, for example, can make a 7 plus oxidation state. And this is because of the involvement of the d electrons. Remember, whenever I showed you that chart, how close those sublevels are to each other? And they can move about more easily and create hybrid orbitals that the other elements can't necessarily create. And you have two different states of stability with those D sublevels. You can have them half full and achieve stability, or you can have them completely full and achieve stability. So the transition elements have a little more flexibility with bonding. Now, although size decreases across the row still, it's not as large a change as the main group elements. And that's the same for going down the group. Size increase isn't as noticeable among the transition elements. Now, iron and many steel alloys that are made from it have been known and used since ancient times. Iron is the fourth most abundant element in Earth's crust and the second most abundant metal. We know that aluminum is the most abundant metal. Iron, cobalt, and nickel have nearly identical atomic radii, so they have similar properties. Iron, cobalt, and nickel are naturally magnetic. And then we have ruthenium, rhodium, palladium, osmium, iridium, and platinum. They all resemble platinum in their chemical properties, and all of them are used as catalysts. Palladium and platinum are typically the most common catalysts, but the others can be used as well. Rhodium, actually, if you have a gold allergy or silver allergy, which is pretty rare, but if you do have those allergies, but you want to wear some family jewelry, for example, you could go to a jeweler and they will coat your jewelry piece in rhodium, which is clear, so that way you could still see the beauty of the jewelry and get the protection from your allergy. Copper, silver, and gold were typically used for coins because they were more rare. They are malleable and pretty unreactive, and in the case of silver and gold, are more rare. You also have copper pipes in older homes. In the newer homes, you don't have the copper, but the older homes you had the copper pipes because it was relatively unreactive, but it was still strong and durable. Now, in chromium, when it's alloyed with iron, you actually get a really hard steel that is corrosion resistant. So it's not going to rust as easily. It can still rust if it not taken care of properly, but it's going to be more corrosion resistant. And they use this steel to plate other materials to protect them from corrosion as well. Chromium, you can see, has 3 different oxidation numbers. So I'm not going to make you memorize them, but just so that you get an understanding of how different the transition elements are from the main group elements, how unpredictable they are. And chromium can form brightly colored compounds such as yellow, orange, blue, green, and violet. It's really a sight to behold. They're beautiful colors. And then we have zinc, which is a corrosion-resistant metal. They have used zinc in pennies before. In World War II, for example, copper, there was a shortage, and so they made pennies out of zinc. Now, its principal use is to coat iron and steel surfaces to prevent them from rusting. And it's used to make an alloy with copper to form brass. And then we have the lanthanides. Cerium is the most abundant lanthanides. It's the principal metal in mish metal. And that is used to make the flints for lighters. Neodymium is used to color and decolor glass. I had a friend who hand blew glass for his lifetime, actually, all that I knew him. He recently retired, and we would go and watch him use make glass and blow glass. And he would describe the process, and he had several different containers to color the glass, and we would go and look at it, and he would explain what elements gave the specific colors. And it was really neat. Like the reddish color comes from, in glass, came from gold. And I found that fascinating that the red glass actually had gold in it because I never would have thought of that before he had explained it. Praseodymium and neodymium also absorb eye-damaging radiation from welding. So they're typically included in your welding masks. And others are used in control rods in nuclear reactors. And promethium is the only synthetic lanthanide. Uranium is naturally occurring. We're in the actinides now. And it's a radioactive element that's used as a source of nuclear fuel. Plutonium is one of the elements obtained from the use of uranium as a nuclear fuel. And plutonium-238 is used as a power source in heart pacemakers and navigation buoys. Californium is used in cancer therapy. So there are many, many, many things that we learn through the use of our elements. If you have questions, let me know, and I am happy to help.